Hello. Uh, so to give a bit of context, this is the first session for the QML case studies track. And to set things straight, this is not quantum machine learning. This is classical machine learning on quantum systems. So hopefully that expectation is clear, and now we can get on with our talk. So who are we? So Qruise is a German company. We build classical machine learning software for the control, characterization, and calibration of quantum devices, not just computers, but any quantum devices. And the primary problem that we are trying to tackle is how do you accelerate the development of quantum technologies. So what problems are we tackling? Quantum technology R&D is too slow. I think everybody in the room will agree. We have been doing this for quite some time. We have, of course, made quite a bit of progress, but definitely not as fast as we would like to have done that. And one of the major reasons behind this slow progress so far is that every step in this research and development process is extremely handcrafted and bespoke. And not only is it handcrafted and bespoke, it requires a lot of human-in-the-loop intervention. You cannot just have a quantum computer and then go home and work from home for the next 6 months trying to improve the device. And even if you do, you'd spend a lot of time logged into your company VPN or your university VPN trying to access the device, because these devices, they don't operate by themselves, they don't improve by themselves. And this translates into extremely slow iterations. So when you go from generation 1 to generation 2 of your quantum device, it could be a quantum computer, it could be a quantum sensor, the time it takes typically ranges from few months to half a year or more. So you cannot really iterate very fast between different generations of your device the way you do, for example, for software, right? So if you are developing a software product, your iteration cycle is much faster, typically in the scale of a couple of weeks or even days. But that's not the case when you're developing quantum computing hardware. You see this large graph here to the right. This is actually a screenshot from a presentation almost 5 years back at this point. This is the calibration graph for the original Google supremacy paper. And you see that what I have circled here is 1 PhD worth of work. And this was the case 5 years back. Maybe now it is half a PhD's worth of work, but that's how much we have progressed. That when bringing up or when tuning up or when trying to characterize a really large QPU so that you can extract the most performance out of it, that's the amount of effort it takes from an advanced physics PhD to get to this point. So what does the research and development process for quantum devices look like? So you start with the design phase, where you design your hardware. This could be a sensor, this could be a computer, this could be any of the different modalities that we have for quantum devices. And once you have completed your design process, you spend some time fabricating. Usually fabrication, depending on which technology platform you're using, may not be that complicated, or it could have a lot of supply chain issues. But once you're done with fabrication, that's where the fun begins, because that's where things start to get really slow. So you spend a lot of time doing tune-up. Tune-up would mean that you want to get to decent gates. You want to be able to do operations faithfully. But even that is not the real fun part. The real fun part is parameter estimation. So what do you mean by parameter estimation? Parameter estimation means that once you have fabricated your device, you need to understand if that device really is what you designed. Because we haven't reached that level of manufacturing maturity in our supply chain for quantum devices, and this affects all of the QML folks here in the room, because this is why your algorithms don't give out what you expect them to give out. That's because we still have a significant delta between what we design or what we want to achieve and what we actually fabricate for when we get these devices out. So this parameter estimation process is time-consuming, extremely bespoke, and requires a lot of very handcrafted, well-designed experiments that you can use to understand what your device actually came out looking from the fab. And once you have done all of this, you want to have something like an error budget. This again goes back to the kind of applications that the folks in the room working on quantum machine learnings are probably familiar with, that depending on how much error you're getting from different sources in your quantum device, that affects the kind of applications that you can do with that device. So different devices have different bottlenecks depending on how they have been designed and fabricated, and you get this error budget basically to show that, okay, these are where I'm getting all these errors from. This is coming from classical electronics. This is coming because my fab is bad. This is coming because I don't have good crosstalk mitigation tools. So things like that. So basically understanding where, if you have a 99% fidelity gate, where that 1% is going, who is contributing to that 1%. So you want to do this process very fast, because once you have gathered the error budget, you want to go back and redesign your system. And ideally, you should be able to do this several times a month so that you progress really fast, because you understand, okay, these are my performance bottlenecks. Now I want to improve them, and I have generation 2. But you can't do that very fast right now, and it typically takes, like I said, in the order of several months to go from one generation to the next generation of devices. So what do we actually need to accelerate this research and development cycle? So in our understanding, what you really need are these 3 things that I'll talk about. So firstly, you want to be able to get to a decent performance of your device really fast. So this calibration step of identifying good operations on these quantum computers, this needs to happen fast, because then you are spending a lot less time wasting on how to get good gates. You can get to applications much faster, and even get to the point where you can see the value of your quantum device much faster. Once you have done that, you go back to the step of parameter estimation. So understanding how well you were able to fabricate your device, because that will help you figure out what you need to improve in your supply chain. Do you need to improve your clean room? Do you need to improve your control electronics? Do you need to understand why you are not able to fabricate your devices the way you want them to? And that is possible only when this whole loop is automated. So unless this loop is automated and in-depth, you are not able to do this characterization very fast, because you are essentially bottlenecked by the number of physicists you have in the room who can go to the lab and spend hours and nights working on these devices. And then you want to be able to identify and have this error budget, which tells you that, yeah, 0.5% of your error is still coming from classical electronics, while the remaining half is coming from a bad fabrication process, and that's what you want to improve. So how do you tackle this problem? If these are the 3 things that you need to accelerate this iteration cycle, how do you go about doing that? So Qruise has these library or modules of our offerings. We call it the Quantum Device Optimization Suite. Let's look at what we have actually in it. That's a nice name, but doesn't say a lot. So the first part of these offerings is in the digital twin and the pulse optimization. So I'll talk a bit more about the digital twin in detail, so let's not dive into that right now. But once you have this digital twin and pulse optimization, you have our offering for extremely automated and very rapid bring up and characterization. And because you have these 2 things, you get the real gem of the whole process, which is this error budget that lets you understand these are the factors in my quantum hardware that require improvement, and this is what I should be allocating 2 man-hours, 3 man-months to get real performance benefits. And this all comes because our models are extremely predictive. And when I say predictive models, I mean that these are models that can predict that, okay, if this is what your model is of the device, this is the fidelities that you will be able to achieve. And you want this because that gives you the confidence that, okay, this is the device I want to fabricate, because then this device will give me the kind of performance I need for running ABC algorithm or whichever application you're focused on. So what does this digital twin do? So the digital twin, fancy term, marketing term, it's a model. It's a model of the system, and it's a very accurate model of the system that combines both the classical electronics as well as all of the quantum parts of the system. And it's a pulse level model, meaning that you actually capture all of the underlying physical system dynamics, and you can also include effects of realistic noise and essentially build up a very accurate model of what you have in the lab out there. And this is fully differentiable, so we have a room full of QML people, so they care about differentiability. It's fully differentiable, it runs on CPUs and GPUs, and it's completely platform agnostic. We currently work with all the platforms I've mentioned here. These are the various hardware platforms that we currently have partnerships with different academic and industrial research groups. And the best part about this is you can model what-if situations. And what I mean by that is if you want to understand that, okay, tomorrow, suddenly I have control electronics boxes that are 10x better. Will that really have an impact, or is that not something I should care about? So these are things that you can model very easily with our tool. And once you have all of these in place, you can do your usual things like getting really good pulse parameterization that give you high fidelity gates. You can get very accurate optimization and propagation methods, all the goodies that come with it. So what do I mean when I say that we model the control electronics stack? So, when I say that I model the control electronics stack, this is what I'm talking about, that you get this level of detail when it comes to how much of your electronics is affecting your system dynamics. So as you can see here, you don't get a very perfect pulse shape when you try to run operations on quantum computers. These pulse shapes have various distortions. They have various limitations because, of course, nothing is ideal, nothing is perfect. And the distortions might be both stochastic as well as something that is very reproducible. And we capture both of these kinds of effects. So you have things like rise time, things like bandwidth constraints, and these are all things that probably get abstracted out when you're looking at it from the applications or quantum machine learning level, but this is actually what's affecting the performance of your algorithms. So you need to be able to have the tools that let you model these kind of effects on your system. So our digital twin actually captures this, and we provide this support out of the box. If you are using any of the OEM providers of electronics, you just write one line of code, and all of the information regarding the devices of that provider is included in the simulation. And then you can actually optimize for all of these effects, well, as far as optimization can help. But yeah, please come talk to me afterwards. I'm very happy to chat more about this. So that's the digital twin and pulse optimization. What's there in our automated bring up? So of course, if you're running QPUs in the lab, be it an academic or an industry group, you want to be able to model these systems, and you want to be able to have a very reproducible framework that lets you model, optimize, characterize these devices. And that's what our bring up tool provides you. So of course, you start with some tool that gives you the different system parameters. So this could be system parameters like qubit frequencies, qubit anharmonicities, different coupling factors, but basically everything that an application scientist does not care about and everything that a hardware person cares about. And once you have this, you have a bunch of experiments that your experimentalist friends in the lab are typically performing to bring up these devices. So these characterization experiments, they not only improve the operation, so you get much better gates, but they actually help you understand what are the underlying parameters of the system so that you can use this information to better design operations. And we support a very broad range of experiments. Currently, it's 30+ single and 2-qubit experiments, and always growing. It's multi-platform. And the best part, if you have some very unique experiment that you design yourself, you just come and plug it into our framework. It's not like you have to only use the experiments that we provide. It's a very developer-first platform that is designed for extensibility. And so this graph is very similar to what you were seeing in the first slide. This graph is basically your calibration process that helps you decide that, okay, I first want to do these 1-qubit experiments, and once they are done, then I want to focus on these 2-qubit experiments. So there is this sense of dependency that only after you've finished certain experiments can you perform the next set of experiments, because that's the nature of calibration, and we provide a tool to define this in a very scalable manner. And as any experimentalist in the lab would appreciate, you want to be able to look back on these experiments so you know that, okay, this is what I ran 10 days back, this is what I ran 1 month back. Can I quickly go back and run that experiment again? Yes, it's very straightforward. We have a dashboard where you just go, scroll down to the date, click, run, and the whole thing runs again. And again, these are things that probably some of the applications folk might not care about, but again, if you're in the lab, you really care about why is my quantum computer every day at 4 p.m. giving me really bad gates? Probably because the HVAC at 4 p.m. doesn't work very well. So you want these kind of tools which monitor not just your system, but also the environment, and can help you draw these kind of correlations between environment and system performance to understand what's affecting them. And we provide something that's more of a quality of life tool, which is a private quantum cloud with a Qiskit integration. This just helps because then you can really work in a very collaborative manner. You don't need to tell your colleague that, okay, I'll be running experiments for the next 2 hours. Please don't go to the lab. You can just submit experiments to the queue, and the software takes care of everything. So we currently have this being installed and not being installed in use at the Forschungszentrum Jülich in Germany, which is a multi-QPU test bed. We have several generations of superconducting qubits running on different stacks, different types of superconducting qubits. And we have this running over there. We have I think several tens of users who are currently using this system. We also have other users. I'm just talking about this because this is a public entity, so I'm very free to talk about everything we are doing over there. Please come later and ask me. I'll be very happy to show you experiments that we run on that system. And there we have users who are using all of the tools that I just mentioned. So the next part of what I was talking about was the predictive error models. And these predictive error models are really built using this whole circular loop that I have here. So what's going on in this loop here? So if you see, we have this digital twin here on the right part. That's what I explained previously. Once you have this digital twin, you can run optimizations to design very appropriate, very accurate pulses, which let you do good gates. This is called optimal control. And then once you have these pulses, you go to the lab and you optimize this even more, because your hardware always has certain effects that you cannot capture in your model. So now you have even better gets. So you have gone to 99.99% and everybody is happy, and all your theorist friends are also very happy because they can run applications. But that's not the end of the story. What you want to do is you want to take all of this data, and then you can improve your digital twin. So that's the fun part with this twin, that it's not a static twin. It's constantly learning from all of the experiments. So as your system drifts, as you introduce new changes in the system, the twin keeps learning that because it's always in this closed feedback loop, trying to understand how to better model the dynamics of that system. So you have this nice predictive model. What do you get out of it? Why do you care for it, right? So you get two very useful things out of it. Firstly, you get this error budget. And this error budget, really, I keep talking about it because this is what helps us make progress in the field. Because again, coming back to the analogy I was making at the beginning, that we are currently bottlenecked by the number of people we can put on the effort, right? So the more number of physicists we can put on the effort, the faster we can get to better quantum computers. And then it comes down to a problem of asset allocation. Like, where do I put this physicist so that I can get the most benefit out of their time and effort? And that's what this error budget lets you do. That if I have 20 advanced physicists with a lot of time and effort, if I devote them to this particular 3 problems, this gives me a 10x improvement in fidelity. And that's what you care about, because of course we can just keep working on things that are interesting, but if they don't improve the bottom line metric, then who cares? So okay, I missed the experiment design part. The experiment design part basically lets you understand parameters that you don't have very straightforward experiments for. So you might have learned about Rabi experiments, Ramsey experiments that help you determine very straightforward parameters of the system. But once you have a predictive model, this model can also design experiments to understand parameters that you typically can't measure with straightforward experiments. So maybe very long-range coupling, very long-range noise. These are things that the algorithm can design for you, experiments optimized to learn that. So we used these tools recently for a work with a partner and also at the Forschungszentrum Munich that I was showing you previously, where you have these kind of flux gates, so controlled Z gates. And usually these flux gates have a challenge that they are done with flux pulses, which tend to have a lot of distortion. And the reason that you have these chevron patterns which don't look very nice and symmetric is because these flux pulses, they have distortion, which is a control electronics problem. And we basically designed a tool that can invert this whole distortion to understand which parts of your control electronics you need to improve to get past this. And we used it to significantly improve the CZ gate fidelities. And okay, so I'm in my last slide, I believe, and I have 1 minute, which should be enough. So this is a short note on how actually the software gets deployed and integrated in your system if you're interested in using it. So we have a very flexible model where it can be either completely in the cloud or completely on premises, or a mix of cloud and on premises, because this is how it is designed. It's a very modular system where we interface with the hardware either over the network or over the local or over the LAN, and this all goes through the provider of the electronics manufacturer. And that's the interface that we use. And why do we care so much about this? We care because we know that we're in an industry that is very IP concerned right now. So we provide the tools that everything can be run locally, everything can be taken care of without having to call back to the mothership. You can air gap it, and we will never know what you're running on your system. And that's about it. So if anybody is interested, please come talk to me. I'll be here for the next couple of days till the end of the week. Happy to chat about how you think this could be useful for you. We can understand your problems, and then we give you access to a demo trial version on the cloud, and then we can take it from there. Thank you.